So welcome to the last session of this WiNS seminar of this semester. We are very happy today because we have Giulia Cencetti. I think I'm saying it correctly. Please, you can correct me.
Cencetti. Giulia Cencetti.
Cencetti. Okay, I'm missing.
But it's okay.
Thank you. But thank you so much for being here today. And she is currently a researcher at the Marie Curie Postdoctoral Fellowship. She's working in the center, the Physique, Théorique, with the advisor, the Professor Alain Barrat. And I'm going to leave you the link to her website, which I really enjoy because it's very nice. And you can have a lot of information of her research in there. So without further ado, I give you the stage.
Thank you. Okay. Think you see my slide now.
Yes.
Okay, so thank you for the nice introduction. So I'm going to talk about a project that I'm developing, which goes under this very long name, Temporal Innovative Model for Imitative Network Generation, a framework to analyze temporal networks and generate surrogate. But this very long name can also be simply reduced to timing. And this is a project for which I received funding from the European Union as a Marie Sklodowska-Curie postdoctoral fellowship. The European Union, via these fellowships, promotes scientific development and in the interdisciplinarity. And I'm using this funding to work on network analysis. Also, if some of you are planning to write a Marie Curie project, please contact me because I can share my experience. So in particular, my project is about a method to generate temporal networks that mimic a particular real-world network given as an input. And we will see that the idea is to divide the original network into pieces and then reassembling them together. And when we reassemble them together, we will take into account global correlations and local correlations in a different way. So I don't need to introduce networks to this audience, I think. Just let me see that when I use the word neighborhood of a node, I mean the set of nodes that are connected to this specific node. So we talk about temporal networks. So a temporal network is a network where links change in time while the nodes are always the same. We consider usually discrete time, and so we can represent a temporal network as a set of static networks, which we call temporal layers of our temporal network. Now, if we want to analyze a temporal network, we have two different dimensions to explore. One takes into account the topology of each temporal layer, which, as we all know, can be characterized by many measures, like centralities, community detections, degree correlations, and so on. But then we have another dimension to take into account, which is the temporal one. So we can follow the behavior of each node in time and see how its interactions change and how strong its temporal correlations are. So how the behavior of a node at a specific time depends on the behavior of the same node at previous times. However, when we have these two dimensions, topology and time, the interplay between these two dimensions makes the network analysis a much more difficult problem. And for this reason, here we propose a simplification strategy, which corresponds to decompose the temporal network into small building blocks. And these building blocks include both the topological and the temporal dimension, but small. So we are kind of paraphrasing the first law of geometry, which says that everything is related to everything else, but near things are more related than distant things. So in other words, we assume an egocentric perspective or a perspective that is centered on a node. And for this node, we only consider its neighborhood, ignoring all the interactions that can occur between neighbors. And we consider this neighborhood for just a few time steps. So the number of time steps is a free parameter of our model, but in the following, I will consider it fixed at three time steps. In these time steps, we pay attention to keep track of all the preserved interactions. So for instance, here in this example, we have that the ego node is connected to node A at the first time step, but it is still connected to the same node at the second time step. So we keep track of this continuity because we want to take into to account the duration also of interactions. But we do not save the identities of these nodes, of the neighborhoods, of the neighbors. Just the shape of their interactions. And like this, shape that we call egocentric temporal neighborhood can be encoded into a binary signature. And this is only possible because we are neglecting all the interactions between neighbors. So we are simplifying the problem, but this helps a lot with the algorithm velocity, and it makes possible to analyze also very big temporal networks. Now, these egocentric temporal neighborhoods can be extracted at each time step and for each node of a temporal network. And so let's suppose we do it for a real temporal network and we store all these structures together. So for instance, here for some different temporal networks of social interactions, we report the first 5 most frequent egocentric temporal neighborhoods. So our hypothesis is that these small structures are able to characterize the node's behavior in a network and consequently to characterize the network itself. So we compare these structures for these different temporal networks, and what we find is that here we report the distance between different temporal networks, different data sets, according to the egocentric temporal neighborhood that we found there. And we observe that if different networks actually display different egocentric temporal neighborhoods, we notice that similar environments display similar structures. For instance, different high schools display similar structures even if the data involve different people. They are also similar to the universities, but we see that they are different from the working places. And they are much different with the environments of children, like the primary school. So this was just the first analysis that is reported in the first paper that we published. But this is just to give an idea of how these egocentric temporal neighborhoods can be representative of a network. So now that we have found a way to decompose a temporal network into building blocks, we can use them. Okay, and how we can use them? We can generate a new network. So first of all, this will be a test to understand if these building blocks that we choose really contain some fundamental information about the network. In this case, the new network will be similar to the original one. Then, if it works, the new network will preserve many of the characteristics of the original graph and could represent a suitable replacement to it. So a surrogate is, for instance, useful when we deal with social data and we do not want to share sensitive information about individuals. Moreover, surrogate networks can be useful for other applications like data augmentation, because in general, for many applications, we need big data, while we often have access to only smaller available data. But I will go back to the application later. Now, let me explain the procedure to put together all these pieces. So I will need to go a bit more in the details, but it's okay if you don't get every detail, you just take the main idea, okay? So first of all, the neighborhoods are extracted for all the nodes and all the timestamps in the original network by using a sliding window over time. And we will generate the new network step by step and node by node. So first, we need a tool that, given the connections of a node for two temporal layers, tells us how the neighborhood in the third time step should be assembled. So this is a dictionary that classifies neighborhoods according to the first two time steps and stores all the possible third steps with their frequency of appearance. So for each key of length 2, representing the beginning of an egocentric temporal neighborhood, we have a probability distribution on all its possible prolongations. And this probability distribution reflects what we found in the original network. Now, let's suppose that we have generated the first two time steps of our new network, of our surrogate network. And I will come back later to how we generate these first two layers. Let's suppose we have them now and we want to generate the third one. So we take one node of this network and we consider its neighborhood for the last two steps. We look for this shape into the dictionary and we sample a possible prolongation from the associated probability distribution. Note that the third step, this third layer that we are adding, will include the prolongation or not of the previous interactions, but it can also include novel nodes that are not present in the first two steps of the egocentric temporal neighborhood. And thus, their identity is not known, and we signal it with a question mark. And these are called stubs or open links. Then, now that we have the neighborhood for this node, the neighborhood that this node would like to have in the third step, we represent it like a directed neighborhood, and we put it into our new layer of our temporal graph. And it is the links are directed starting from the ego node, and they reach the nodes that this ego node would like to have as neighbors. So each directed link represents a request of connection. But we don't know at this stage if this request will be reciprocal or not. So this is just temporary for now. Then we do the same procedure for each node of the network, and we obtain a possible third layer, but which is so far provisional because all the links are directed. Now we have to validate them or not. So since they are directed, only half of them should be validated. So first, we validate the bidirectional ones, which represents the reciprocal request. Then for the unidirectional ones, we randomly choose half of them and we validate them. And finally, we randomly connect the stubs. The stubs are open links, so they need to find their other half. And we do it randomly. So we repeat, at this stage, we have generated the third step, the third temporal layer of our network. Then we can repeat the procedure for how many steps we want. So there is no limit. Impossible we can obtain an infinite number of temporal layers. And we obtain our temporal network. So now let me take a step back. At the beginning, I told you, let's suppose we already have the first two layers and then we generate the third one. So how we generate the first two? Well, it is actually the same method, but just rescaled. So in the first layer, we obtain it with a configurational model. So it's a model that the configurational model, it's a model for network generation where we can a priori specify the degree of nodes, and we choose the degree of the first layer of the original network that we want to imitate. And to generate the second layer, we apply our procedure with the dictionary and so on, but just rescaled. So the dictionary will only have keys with only one step and not two. And so it is exactly the same method, but with only one step as input. So when we have this procedure, we can generate some networks. Now, do you correctly see? Because I have the bar just on my, oh, sorry.
I think we can see the whole slide.
You can see everything.
So, okay. Yeah, it's fine. Thank you.
Because I cannot move it. Okay, so when we generate our new network, here I reported some results. So I reported the number of interactions in for each network in time. And here you can see that for each of these figures, I reported a black curve, which represents the original network that we want to imitate, and an orange curve, which represents what we obtain with this method. And so we see that we are able, with this method, to reconstruct the correct number of interactions in time. To do so, we also used the procedure that I just explained, but instead of using a unique dictionary for the entire network, we use 24 dictionaries, one for each hour of the day. So like this, we can reproduce the day and night temporal periodicity. Now, when we have this method, we can also generate a temporal network that, even imitating a real one, has a different dimension, both in terms of length, of temporal length, and also in terms of number of nodes. So I mentioned before that the problem of data augmentation, it is It's a problem because original data, especially when we talk about social data, are often incomplete, or they involve only short intervals of time, while for many simulations we need big data. For instance, if we want to simulate an epidemic model on this network, if we want to see the long-term behavior of an epidemic, we need a network which is long enough. And the same if we want to see how an epidemic moves into a population, having a too small population is not useful, is not informative. So, with this method, as I was saying before, since we generate each temporal layer step by step, then we can generate any number of temporal layers for our new network. So it's easy to generate even a longer network that imitates a shorter original one. So let me show you an experiment. This is the original network of a workplace dataset. And this is, we see that the length is 2 weeks. We have 10 working days. And we do this experiment. We just cut this temporal network, and we suppose we only have access to the first part, only to the first week. Then based on this, we generate our surrogate temporal network, and we make it longer, 2 weeks long. So at this point, we can compare it with the original one, and we see that it is actually working quite well. Similarly, we can increase the number of nodes. Because, as I was saying before, it is useful to have large populations, but also because sometimes data are not complete. So let's suppose this is the original network of a high school. Let's suppose we only have access to half of the population in this dataset. And so the number of interactions that we see, it's just this. And based on this, we try to generate a new network that has the correct number of interactions, that has the double the number of nodes. So, we generate these and we can compare it with the real one, and we see that we are quite able to reconstruct the good number of interactions. And of course, we can do the same, we can do both at the same time. So increase the time and the size of this network, and this is what we obtain. Then, since we wanted also to compare our method with state-of-the-art models, we used 3 other methods for surrogate generation. 2 of them are based on temporal motifs. So the idea is quite similar to ours, because temporal motifs are significant segments of a temporal network. And another one is based on deep learning. And when we observe the number of interactions in our network and the other methods, we see that our method, which is the orange one, is the one that better recovers the number of interactions in time, the one that is more similar to the original network. Also notice that for one of the methods we already reported in the insets, because the number of interactions that it was obtaining was on another scale with respect to the original network. Then we can also compare the distribution for each temporal layer of the number of interactions, the number of interacting individuals, and of new conversations. observing that this method is quite good in recovering the original distributions. And here we have the duration of interactions and the average shortest path length on each static layers and the number of connected components. So these results have already been published in a paper, but there is still some work to do, because as I was saying before, these puzzle pieces that we are considering are very small in terms of topology and time. But this allows us to obtain a very fast and scalable model which only retains the minimum amount of information. So the general networks, the networks that we generate will be very similar to the original one in terms of short range and short range and short scale in time and topology. Sorry, I got a bit lost. So the new network that we obtain will be quite similar to the original one in terms of short range and short scale topology, but it will miss all the larger correlations. In fact, we know that in real networks, we have long range topological correlations and long-term temporal correlations. For instance, for the topological dimension, we know that, for instance, in social network, if I have a connection with a node A and A has a connection with a node B, it is highly probable that I have a connection with B too. In other terms, in social networks, friends of my friends are my friends too. And this is called clustering, and it is measured by counting the number of closed triangles. And we know that in social networks, we have usually a high clustering. And also we usually have modularity, which means that nodes are organized into communities or groups. But in the networks that we generate with this method, we are not able to reconstruct these features, neither clustering nor modularity. So let me show this. Here you can see in the middle, there is the original one, the original network of a primary school, and we see that we have a modularity. This is this network has a high modularity because children are divided into classes. But when we generate our surrogate network, what we obtain is the network on the left, which has no modularity. Actually, the modularity index in the original network was around 0.6, and what we obtain is around 0.06. The same for the clustering. Here in the plot, you can see the distribution of clustering for each temporal network, for each temporal layer in the original graph, and in black, and in orange, the clustering in the network that we generate as a surrogate with the egocentric temporal neighborhoods. And we observe that the clustering is much smaller in our generated network. So how can we correct this feature? Well, you remember this, the step in the generation part where we were validating the layer connections, we passing from a directed network to an undirected one. And if you remember, there were two steps which were random. We were randomly validating half of unidirectional edges, and we were randomly connecting stubs. So we can modify this validation procedure in order to insert a preferential choice that tunes clustering and modularity. In practice, I can set a higher probability to choose couples that have common neighbors, such maximizing the clustering, and also choosing with higher probability couples where the two nodes belong to the same group, where here the groups are defined from the beginning and extracted from the real network using the Louvain algorithm to find communities. So with this, we can maximize clustering and modularity. And the result is this. So inserting these long-range spatial correlation or topological correlations allows us to obtain a clustering distribution which is quite similar to the original one, and also a modularity which is a good approximation of the real one. Also, we can look at these quantities in time. So, for instance, here in the first plot, you see the number of interactions in time, which is reported, as always, in black for the original network, in orange with the initial procedure with the egocentric based only on the egocentric temporal neighborhood, and in green the same procedure where we added long-range spatial correlations. And you see that for what concerns the number of interactions, nothing changes, while the modularity is increased by this addition, and the clustering too is very much increased. So going back to this, we were taking care of the topology, but we also want to reproduce long-term temporal correlations. In fact, in a real social system, if I have a friend, the probability that I interact with my friend at a specific time t is higher than the probability that I interact with a random person, even if it is some days that I don't talk with my friend. So we need memory in this procedure. While the model, as I was explaining it until now, has only a very short memory, which is given by just the temporal size of the puzzle pieces. So here it was only 3 steps. So at some point, if I don't talk with my friend for some time steps, at a certain point, I have the same probability to interact with my friend and with a perfect stranger, and this is not realistic. So we want to insert memory. And how we do it? Again, as we inserted clustering and modularity in the validation process, we can also add memory to this preferential choice. In practice, I set a higher probability to connect 2 nodes if they have already met in the past, and proportionally to the number of times that they met. So while I generate the network, I store the contacts between all nodes in a matrix of memory that will be progressively updated during the network generation. And I will use, during the procedure, during the network generation, I will use this matrix of memory at each time step to set this preferential choice, and such reinforcing the connections that have already appeared. So this that I'm reporting here is just an example of how it can appear at the end. And you can notice here that the connections are not homogeneously distributed among all the nodes, but there are groups of highly connected nodes that take shape when we generate the network. And this is something that we observe in real networks, but we couldn't reproduce with the old method. And this can be seen, can be quantified by observing the distribution of weights in the aggregated network. The aggregated network is the static network that I obtain when I put all the temporal layers of a temporal network together. And I assign to each connection in my static network the number of times that connection appeared in the temporal layers. So these are the weights of my aggregated network, and these are in practice the distribution of the elements of the memory matrix that I was showing before. So we observe that from this plot that in the one on top, that in the original network there is an heterogeneity of weights, while in the surrogate network that we obtain with the first method, we do not observe this heterogeneity, but the weights are quite homogeneous. Then the situation is slightly better when we insert the spatial correlations, but we need temporal correlations to have a good approximation of real behavior. And below, in the plot below, you can see the number of interactions in time with the original network, with the network which is only built with egocentric temporal neighborhood, and with the one with long range and long-term correlations. And if you are concerned about what happened to clustering when we inserted memory, well, it is still good and very similar to the one that we were observing before. Then another modification that I made to this process is that instead of considering 24 dictionaries, which were one of each hour of the temporal length of the graph, which seemed like a reasonable strategy, but a bit arbitrary, I am now dividing the temporal network into temporal states. And these temporal states are based on the similarity between temporal layers in the original network. So for instance, here, for the primary school, I can see that there are clearly 3 states. One for when the kids are in the classrooms, one for the break, and one for the nights when they are not at school and there are no interactions. And so I can use this partition to generate dictionaries and to insert long range and long-term correlations. So in a certain sense, it's the network itself that tells me how I should choose the time intervals to generate the surrogate network. And here, this is my conclusion. It's still work in progress, so I don't have a publication for the last part, but I can recall the first 2 publications related to this idea, and I thank you very much for your attention.
Thanks. Thank you so much to you for presenting in this seminar. Thank you for that. We can still see the whole screen if you want.